So, hello everyone, and welcome to another ICTS virtual string seminar. We are happy to have Justin from IIC with us today, and he's going to tell us about information theoretic measures in 2D CFT and their universal properties.
Yeah,
Over
so
to you, Justin.
thank you for the invitation, and it's nice to be giving a talk. But it's actually nicer to be at ICTS and giving the talk. But we have to make do with this, I guess. So I'll be talking about information theory in 2D CFT and their universal properties. I'm sure. I mean, there have been many talks on these topics, but perhaps I'll try to do something different. Uh, so. It's work done earlier with Barsha, who's a student at ISC, and Shavik Datta, who's now at CERN. And then there is some ongoing work, which I will come to towards the end in this talk. So let me start with some introduction. And I mean, the introduction is basically there is these measures, entanglement entropy, relative entropy, modular Hamiltonians. We will define them, at least we'll define the first three, and trace squared distances. They play, recently they've been playing very important roles in holography, quantum field theory, and black hole physics. So here in this talk, what we wish to do is to study very simple properties of these measures in 2D CFT. And what is special in this study is that the 2D CFTs admit Virasoro symmetry. So how is these measures, how are these measures sensitive to Virasoro symmetry is the question we would like to ask. How does a single interval, for instance, a simple question is, how does a single interval entanglement of states created by primaries and descendants differ? I mean, descendants are obtained by acting, Virasoro operators on the primaries, and how does the entanglement properties differ? That's one question. This is another question, again, related to the fact that we are in 2D CFT. So in 2D CFTs, you can deform the theory by holomorphic conserved currents, I mean, of this kind. Okay, J is some holomorphic current. And one can consider the thermal density matrix given like this. And by this deformation, the thermal density matrix gets deformed to something of this kind. And then again, how are information theoretic measures sensitive to these deformations? A part of this question has been addressed earlier. I will allude to that later, but here it's sort of a new question we will look at. So while studying these questions, what we will try to focus on is to extract universal properties with the aim of studying them in holography. And I will talk about that towards the end of the talk. So first, let us go through the measures. So the measures and how to define, how to evaluate them, define them as well. So entanglement entropy, I think many people must have heard about it. So I'll be very quick. So we consider a density matrix of a quantum system, partition the Hilbert space into two disjoint sets of commuting observables A and B, and then define a trace over one set of observables, say B. Okay. And the entanglement entropy is just the von Neumann entropy of this reduced density matrix. Let me just close the door. There is the von Neumann entropy of the reduced density matrix. And in quantum field theory, one usually chooses A and B to be complementary domains of a spatial slice at a given time. Okay. And the trick to the strategy to evaluate the entanglement entropy, is usually relies on this identity, and it's known as this replica trick. The identity is the following: you take this trace of this reduced density matrix, which we had defined, to the nth power, and take this following limit. And by some algebraic manipulations, you can show that it in fact reduces to the von Neumann entropy in the n equals 1 limit. Now, so let us consider the basic quantity we are looking at. So consider 2D CFT on a cylinder. For convenience, we take O, O to be a primary of only holomorphic dimension, h, 0. I mean, this can be generalized to h, h bar or h, h. Just for convenience, I'm taking this. And we construct a reduced density matrix of the following state. The state is basically O acting on the vacuum. Okay, so that's the state. And this is the density matrix. And I take the trace over this region B. I will tell the region B soon. The O dagger, the bra and the ket is formed by, O dagger, which is the BPC, or the Belavin-Polyakov-Samolishkov conjugate of O. And the trace is taken over the spatial region complement to the interval 0 to 2 pi x. Okay. So in the path integral, it's easy to visualize this. Okay, there are many words to say, but in the path integral, it's easy to see this. Okay, so this is the picture we have. Okay, I hope it's sort of clear. So it's basically a cylinder. So the conformal field theory is on a cylinder. And then we have a state, the excitation, is created at t is equal to minus infinity to create the state. And the ket is basically phi at t is equal to plus infinity. And then the trace sews these cylinders together and except for the region 0 to 2 pi x. Okay, so that's the interval 0 to 2 pi x. So the trace sews them together, but we don't take the complete trace. We leave the 0 to 2 pi x outside, untraced. Then this is rho A, okay, and then we take trace of rho A to the n such cylinders. And how do you do that? Basically, in the path integral, you glue these n cylinders, okay, such that these mouths are connected. Okay, the top surface of the mouth is connected to the bottom, and so on. It's connected, and the last one is connected back to the first one. Okay, so that's trace rho A to the n in the path integral language. Now, this branch cylinders is a cumbersome language to evaluate anything in. So what we can do is first go over to the plane. Okay. So to evaluate this path integral, first you move on to the plane. Okay, so the plane, to go to the plane, we actually use the conventional, cylinder to the plane map of this kind. And you can see that the starting point is equal to minus infinity actually goes into the origin of the plane. You can see it just from this map. And t is equal to plus infinity maps to infinity on the plane. And the slice, t is equal to 0. At t is equal to 0, we had this slice in which we actually evaluated the reduced density matrix by tracing over. So t is equal to 0 slice is mapped to the unit circle. You can see from here. And there is an interval which we didn't trace over, the 0 to 2 pi x. That's basically the small segment of this unit circle. And the endpoints of the circle of these segment are these 2 points. And these n branch planes are sewed over to these over the segment of this kind. So this is not a good picture, but so this is sewed over kind, over this segment of that circle. Now, even this is not very convenient to evaluate anything in. So what we do is we actually, map all these n branch sheets to one sheet of the complex plane by something called the uniformizing map. So here is the map. You can see that I'm taking the nth one by n. So basically a plane goes into a 2 pi by n wedge, okay? And you can see that, the branch cuts, okay, where, the u and the v points of the branch cut. So if you, for instance, if you substitute u, w becomes 0. If you substitute v, w becomes infinity. So the branch cut is basically a line which starts from the origin to infinity. Okay, these points, so these points, the points where where this operator was, which was at 0 and infinity, are mapped to these points. You can put 0, for instance, because of the nth roots. There are n possibilities of this kind, and then x, by the way. Okay, so I didn't define x. So x is u is equal to e to the power of 2 pi x, basically. So the points at which the operators are now actually are on the unit circle. So now it has become, the picture is like this. So here is the the cut. The cut becomes this full line. Okay, and the operators, which was at on the cylinder, it was at t is equal to minus infinity and t is equal to plus infinity. or on the segment un, v becomes at this point e to the power 2 pi x n and the shifted point here. So they are lying on the unit circle. So the operators are on these unit circle. So essentially the path integral now is a correlator, a 2n point function correlator on this plane. So to evaluate entanglement entropy of an excited state of a state, you will have to essentially evaluate this 2n point function. Okay. And so therefore, from the path integral, we see this following: that trace of rho a to the n, this is the normalization without any insertions, trace of rho 0 to the n. This is basically just the branch sheet, is essentially this 2n point functions. And the 2n point functions of these operators are such that all these maps have to take into account, and the maps are these, and therefore the appropriate conformal transformation have to be taken into account to evaluate these correlators. So if you successfully evaluate these correlators, then you can say something about the entanglement property of this excited state. So that's the definition for the entanglement entropy of an excited state. Now, so let me again say, this is a more descriptive version of that. This is basically a 2n point function on this branched, on this uniformized sheets. There is a pair of O's at every wedge, just to keep in mind. And this one is basically the partition function of without any insertions. Now, the rho a 0 to n, this is the branch sheet without any insertion, just the vacuum. This is basically the vacuum entanglement entropy. This can also be evaluated, though I won't go into the details. But this results in this following expression. But we will be interested in the excitations about that. Okay. So the relative entropy is the following functional. So it basically returns a number given two density matrices. And here's the formula for that. Basically, this part is almost like the von Neumann entropy, the first term. Okay? And then there is a relative to that. Basically, it's log of rho 1 by rho 2. So, and it has various properties. There are very interesting properties to it. For one instance, which we can see in all these our calculation, it is positive. Okay. And recently, only I have found that there is this mini introduction to information theory by Witten, which is very useful. He has done all the proofs, basic proofs from scratch, actually, which one can study from here. Now, because it is positive, it's actually a measure of the distances between the density matrices. Okay, and in our case, we will be taking this rho 1 and rho 2 be these reduced density for reduced density matrix for single interval for say two different states in a CFT. And we can get a little bit more intuition about this relative entropy by introducing this modular Hamiltonian. Essentially, it's a log of this rho. And just by this definition, the fact that H is minus log of rho, you can rewrite the relative entropy in this manner. Okay, so here it's just substituting for the logs. Okay, so this is the rewriting of it. And you can see from here, this part is the von Neumann entropy type term, and this is the another term. And in fact, this term basically it's like expectation value of the entanglement entropy of the second state in the density matrix of the first one, which can be evaluated best by the sum, for instance. Okay, and going along this way, if you define free energy, okay, analogous to the thermodynamic quantities, like E minus 2s, okay, Ts, this is the following. So E is like expectation value of the H2, say, second state with respect to the density matrix of the first one, minus the von Neumann entropy, okay, and this is the von Neumann entropy. And you can actually rewrite the relative entropy as differences of free energies of these two density matrices. So the relative entropy is basically the difference of these free energies. And so it is analogous to the thermodynamic quantity with, with rho 1 as the, which is e to the power minus h1, this density matrix as the equilibrium.
Can I ask a question?
And Yes.
So there is no parameter analogous to temperature in this.
Yeah, you can introduce that, but this is just even for states without any temperature, just for states actually. So you can introduce that. In fact, later on I will introduce it, but you can define all these concepts without the notion of the temperature, just for states in the CFT. Yeah.
Okay.
Yeah, in fact, here you can say beta is 1, the way it is seen. But you can also define it for thermal states. You can talk about relative entropy, which we will talk about, between two thermal ensembles. And you can define all these concepts exactly for that even. So the positivity of relative entropy is analogous to the statement that, in fact, it's always positive, and the system achieves equilibrium when the free energy is, minimized or vanishes in this case. That's a possible case. So
sorry, Justin.
Now how to evaluate this relative entropy?
Sorry.
Yes.
Justin, I just missed H2 and H1.
Oh, yeah. So they were just defined as this. Minus log rho 1 and minus log rho 2.
Hamiltonians.
So you just use this same definition and just put H1 instead of, for instance, log, and H2 instead of log rho 2.
Thanks.
And then you get
defining the generalized free energy of it was rho 1 H2. I mean H2.
The second state
with respect to the state rho 1. So okay, so that is what you mean by F rho 1 with argument rho 2.
Rho 2, yeah. Right, yeah. So it is like, that's the meaning of that, because rho 2 is corresponding to H2. Yeah. So it has this close resemblance to the free energy. And what is the replica trick for evaluating it? It's very similar again for the entanglement entropy. It's basically this formula. So you raise, the first term, you remember one term was like rho log rho. So that term you could use the same approximation, same identity what you did for the von Neumann entropy. And the second term is the following, rho 1 rho to the n minus 1. And in the limit n going to 1, you can convince yourself that it actually becomes the relative entropy. So therefore, we can actually get a path integral description for this reasonably easily, because we had the path integral description of this, which was n cylinders. And at the end point of each of these cylinders, we had these excited state. So here, suppose we consider the following. Rho 1 is basically the reduced density matrix of the operator O1. Rho 2 is corresponding to the reduced density matrix of operator O2. So these reduced density matrix, as I described earlier, it is basically, you trace over the whole part, except that mouth on the t is equal to 0 slice. So the path integral representation is the following again, except that in the first, so it's the same as before, except that in one of the, the second term, basically the one of them you have O1 and the other one is all the other same operators. So you'll have to evaluate, and if you go over to the uniformization surface, so you have to evaluate this 2 endpoint function in which in one of the wedges there is a different operator.
Excuse me, sir.
Yes.
I have a small question. So for the n-sheeted path integral, usually there is a geometrical description of n torus or the Riemann surface.
Right. So for getting the torus, for instance, here, you need two cuts. Like for instance, n equals 2 surfaces with 2 cuts is a torus, but this one is still a plane. With 1 cut, it's still a plane.
Okay. Yeah. Thank you.
So in terms of this correlator on the uniformized plane, you just see that okay, there is one on one of the wedges. Basically, it's the O1, and in all the other wedges, it's the O2 operators for this particular case. And therefore, this relative entropy can be obtained as a limit of this ratio of these correlators. So we have to take these ratio of these two endpoint functions. If you're powerful enough to evaluate this and take the n going to one limit, you will be able to get the relative entropy. Okay, and by doing this, actually, the rho naught, with the vacuum entanglement entropy, that cancels, and so therefore there's no cutoff dependence in this particular quantity. Okay. Now, okay, so let us see the most simplest example that we have, the free scalar theory, right? And you have a primary there, e to the ILX. X is the free scalar, and you have this primary e to the ILX. And let us evaluate, the reduced density matrix and evaluate all these quantities. Now, so this is the state which we are looking at. Actually, there is a dagger here. You have to understand there is a dagger. There is basically a BPZ conjugate here. And if you think about the two endpoint functions, you require correlators of this kind. Okay, there is n of them with plus IL and minus n of them with the minus IL. And that correlator is known. It is this. It's given by this particular expression of products of various these insertions, points of insertions. And because of all the conformal transformations involved, you need also these Jacobians of the conformal transformations, and particularly at these points. Initially you started out at 0, one of the operators was at 0, one of the operators was at infinity, and you'll have to evaluate them at 0 and infinity. And so these are the slopes of the conformal transformations. Now, if you put all of these together, and it's actually a surprise, if you put all of them together, the entanglement, single interval entanglement entropy of this thing, the ratio of these two objects is actually 1. I mean, it requires a lot of manipulations and identities of nth roots of unity. And if you do that, it turns out it's 1. So this excited state, I mean, though it was reasonably, it looked like, okay, we have a nice, interesting problem. But it turns out that the entanglement entropy of this excited state is identical to that of the vacuum. You don't see any features. Okay. So therefore, the change of the entanglement entropy due to this excitation is in fact 0. But let's go ahead. So the relative entropy can also be evaluated, but that is non-trivial actually. And it is this particular, I hope the procedure was clear how to evaluate this. And given this particular CFT, it's just a matter of computation of evaluating these correlators. And so the relative entropy of these, the state e to the ILX and the vacuum is the following expression. And since the sum, if you remember, if the sum of the relative entropy and the relative entanglement entropy and the relative entropy results in the expectation value of the modular Hamiltonian, okay, you actually get the modular Hamiltonian in this particular state. So this is the formula. And you can also evaluate, relative entropy of two excited states. That is of this kind. Okay. So, so that's sort of, it's a tractable model. You can evaluate. We'll come back to this model again. So in which you get sort of a feel about these quantities. Okay. Now let us look at relative entropy from another point of view. Okay. From that of an Euclidean quench. So we'll come back to that point of view again. But first, let's look at this point of view again. So then, again, this relies on another identity of, getting the relative entropy. Here is this following identity. So it's basically trace of rho 1 to the alpha and rho, the second matrix, to the 1 minus alpha. And if you take the alpha going to 1 limit, here, again, you will get the relative entropy. And here you want, if this particular alpha is in this domain, okay, between 0 and 1, we can represent them as a quench, as an Euclidean quench. And this was introduced by these authors soon, these authors in 2018. And I will show it soon actually how this is actually an Euclidean quench. Okay. So I hope this identity is clear. Again, you just have to imagine differentiating with respect to alpha And if you imagine doing that, you will get the relative entropy. It's a simple calculation. Now, so what we will consider is basically ρ2, that is this state, to be the thermal equilibrium state, e to the power of minus beta, and ρ1 is the deformation of the density matrix of this kind. Okay, J is some operator. And the Rene divergence, if you look, this is also called, I forgot to introduce that word. So though it's a relative entropy with parameter alpha, so it's also known as Rene divergence. Okay, so the Rene divergence as a path integral can be described as the following. Okay, so essentially you have a Hamiltonian path integral on the cylinder, because the trace is taken over the cylinder. And over part of the Euclidean time, alpha, beta, the Hamiltonian H prime, which is the deformed Hamiltonian, is switched on. And the rest, it is the original CFT Hamiltonian. Okay. And if you can evaluate the path integral on this particular cylinder, in which there are these two Hamiltonians or two actions, then you can in fact evaluate the Rene divergence, and therefore take alpha equals 1 limit and take the relative entropy, find the relative entropy. Now, so let's formalize this a little bit. So the path integral on the thermal cylinder with the Hamiltonian HCFT deformed by this operator J can be thought of as this path integral, and there is this the operator J is coupled to a time-dependent source, Euclidean time-dependent source of this kind. So this is this heavy side step function. Basically, this switches on and this switches off, and that is this path integral. So the path integrals, one needs to, so since these are not normalized, you have to normalize them. So the path integrals which you need to evaluate are the original path integral, okay, the deformed path integral, minus bu beta j, and also the time dependent, basically when this is switched on and switched off, that path integral. So, and if one knows all these path integrals, one can just substitute it and evaluate the Rene divergence, sorry. And here is the formula again. So this is because of the normalization. So I've introduced the normalization. So trace rho to the alpha, rho beta to the 1 minus alpha, and then this. And since it is formulated in this path integral, if you can do, if you want to think of mu as a perturbation, and if you can, evaluate all these in perturbation theory, that is also useful. So you can, if you're successful in evaluating perturbation theory, that is a method to evaluate Rene divergence. And that was what Myers and all do. They evaluate these in perturbation theory. Now, what we noticed is that there are some exactly solvable problems in this setup, and I will introduce them in increasing order of complexity. So suppose the J operator, which we introduced, commutes with the Hamiltonian. Okay, then we have the following simplification, because so this is rho alpha, it's the same rho. So one of them is rho and one of them is just rho beta. Rho is the excited one. So if it commutes with the Hamiltonian, okay, then you can just put them together, okay. So it's basically, you can just raise them and put them together. So it's basically a partition function of the theory in which the, the chemical potential for that, turned on operator is just scaled by alpha, okay, because it is not part of 1 minus alpha. So if the Hamiltonian commutes with J, you can just put them together, you can raise them and put them together, and this is what turns out to be it. And so therefore, if you know the partition function of the deformed theory, then you can evaluate Rene divergence. And so this is what, so if you consider the following deformations, these are conserved current deformations. So you take the CFT and you deform by conserved currents of this kind. Okay, so this is the U1 conserved current, this is the stress tensor conserved current, And this is the spin 3 conserved current. So in all these cases, the Hamiltonian's deformations commute to the Hamiltonian. These operators commute to the Hamiltonian. And in fact, you can evaluate the Rene divergences, because you know how to evaluate the partition functions of these theories. Okay. In this context, I want to mention that, okay, though we are evaluating a different quantity, Rene divergence, which is a little bit different, but the entanglement entropy, which is very simple, has also been, evaluated under these deformations earlier, and there are universal terms there too. So, but here we are focusing on the Rene divergence. Now, here are the results. So for the U1 current, the result for the Rene divergence is really simple. It is this particular formula. And where the coefficient of the OPE, this is only information which comes out, the coefficient of OPE is sitting there. Now, Rene divergence is this functional have certain properties. They are like they're supposed to be positive, they are concave in some way, and they're increasing in alpha. So all of that actually we check every time we get a function, and it is satisfied. Okay, so this is a very simple one. U1 current is really simple. Now, this is a little bit more interesting, and I'll come back to it again. So the deformation of the stress tensor can be actually shown to shift the temperature of the system. Okay, so so here it shifts the temperature of the system, and you can actually show this from perturbation theory. Actually, you can calculate order by order. You can also imagine. First you can calculate order by order, and then look at the partition function. And you can notice that each order changes the temperature by just this particular shift. That's one way of doing it. But just by thinking about it, this is a stress tensor, and so it is changing the the thermal circle in some way. And by just thinking geometrically, also you can sort of guess that this shifts the temperature. And this is mu t actually, and so. And from this shift, you can see that this for the temperature to be positive, we are restricted to this particular, these shifts have to be, this mu t has to be less than 1 by 2 pi. And the Rene divergence, which actually evaluates distances between two thermal states, is of this kind. So you evaluated, this is a formula, you can see that T prime is the temperature associated with rho, because we saw that the deformed matrix is also some thermal matrix, actually thermal density matrix, and this is the particular formula for that. Okay, and there is a formula here. I will come back to this, but this is another exactly solvable case. And certainly for the spin 3 deformation, also these partition functions with the spin 3 chemical potentials turned on are known, and just by using that we can evaluate the Rene divergence, and this is the formula. Every term can be found, and you can write down a complete formula for it. Now, what is the applications? I mean, what were the motivations for introducing this by by Myers, and then what was the usefulness of having this exact results? So actually these Rene divergences are useful to generalize laws of thermodynamics in open systems, and that's what Myers and all looked at it. So these laws, these generalized laws state that a transition from density matrix rho 1, so in a transition from rho 1 to rho beta, so rho 1 to this thermal state rho beta, another state rho 2 can occur, okay, only if the potential, or S this object is higher than this Rene divergence is with respect to rho 1 is higher than respect to rho 2. So this is basically the generalization of the differences in free energy, but the differences in free energies or generalized free energy is alpha equals 1, but this is generalized to all alpha. So you demand this inequality for all alpha, and that's the generalized laws of thermodynamics which they proposed actually. And so this statement reduces to the differences in free energies of this rho 1 and rho 2 at alpha equals 1. And that can be seen from that connection which I had mentioned about the relative entropy being related to the free energies. Now, the second law in principle is a stronger constraint. I mean, the question is whether if this alpha equals 1, if it is positive at alpha is equal to 1, is it true for all alpha? But, or it is guaranteed to be true or not. I mean, whether this has more constraints or not. And indeed it does. Actually, from these simple exact results, and as well as some other results which I'll point out, we can actually show that there are transitions which are allowed at alpha equals 1, but prohibited in general by consideration of all alpha. And here's an interesting one, which I can just state in a very simple way. Okay. So consider CFT at temperature T prime. It's a subsystem, and it's contacted with a bath at temperature T, and T prime is bigger than T. Okay, and of course, then the system will relax to, of course, T. And the conventional second law, traditional, says that all in this transition, okay, all these temperatures, the temperatures have to be, which are bigger than 2T minus T prime are allowed. Okay, so these are allowed. But so basically the average of these two is T, the bath temperature. But the generalized second law, actually, if you go through this analysis, using the Rene divergence evaluated, the exact Rene divergence evaluated, shows that, T prime, all the transition temperatures which are allowed have to be greater than the T squared by T prime. Okay, T prime is the starting temperature and T is the bath. And the generalized temperature, is bigger than T prime. So there are certain laws which are certain temperatures, lower temperatures, which are not allowed, just from the fact that arithmetic mean is greater than geometric mean. So there is, you can see there is this arithmetic mean and geometric mean coming up. So in principle, I mean, if these generalized second laws are to be believed, that there are restrictions, and these restrictions could be found from these exact relations. Myers and all had to work very hard because they could not, they had results in only perturbation theory. But here, from the simple result, I mean, from this exact result, we could make this statement.
Justin?
Yes.
So this second relation comes by checking, I mean, it follows for all alphas, is it?
Yeah. Second, this condition comes from by checking for all alphas. Yeah, it's a very simple, I mean, how it comes, it's quite a simple, nice relation, how it comes. Now, so let's go to more complicated deformations. So let's look at deformations which do not commute with Hamiltonian. And now we start with a toy example. This is a very simple toy example. So this is a simple harmonic oscillator, and it deformed by this linear term. Of course, this is exactly solvable. You can find the partition function and so on. But this deformation doesn't commute with the Hamiltonian, okay, meaning p squared because it's x. So, and to evaluate Rene divergence, we can think in terms of the path integral. It's easier to think in terms of the path integral. And it basically amounts to, in the path integral, promoting mu to this time-dependent object, this object in which this is turned on and turned off. Okay. Now, the path integral of a time-dependent forced oscillator is exactly solvable. And that's something from Feynman and Hibbs is exactly solvable. And here is the result for Rene divergence. Okay. So this is a more non-trivial function of alpha, and here's the result for the Rene divergence. And we will see that this behavior is universal for a class of problems. Okay. So let's look at the class of problems. So consider the CFT. So I hope this behavior is, so it's basically, and this functional satisfies the required properties of Rene divergence. So it's a reasonable simple function, product of two sine hyperbolics with the alpha dependence. Now consider the CFT on a size L, okay, on a CFT of size L, and we deform the Hamiltonian. So this is more easier. Actually, there is a way of getting it using just by this integral, but this is easier. So we have the usual Hamiltonian, the CFT Hamiltonian, and then we add these Virasoro generators to it. Okay, so L1 and L minus 1. So we add this. This is the deformation. So again, it's a deformation out of this conserved part of the conserved currents, but it's inhomogeneous because you had this sign cos 2 pi x, and that's how this very particular inhomogeneity which we integrated to get the L1 minus L minus 1. And for NA divergence, we need to compute this object, this particular partition function turned on for alpha, and the usual Hamiltonian, without that this perturbation turned on. Okay, so we need to compute this partition function, and in fact, this partition function can be formally computed exactly, actually. Here is the procedure. Let's just uncluster everything, just to focus on a particular essence. We'll just focus on the holomorphic part, just the holomorphic part, L naught, and this holomorphic part of L minus 1 and L1. So that's this. So let's just focus on the holomorphic part. So we have the original Hamiltonian. This is the deformation. It's switched on for alpha, and the original one is back for 1 minus alpha. Now, these are exponentials of elements of the SL2 algebra. Okay, so basically they are generators, and they form a closed SL2 algebra. Now, using the Becker-Campbell-Hausdorff identity, we can write this whole these exponentials as a single exponential. Okay, so here it is. So you just write this as a single exponential. And if you think about the Becker-Campbell-Hausdorff identity, these result from commutators of these operators. Okay. So therefore, what goes in AM is basically the structure constants of the algebra. Okay. So, the Becker-Campbell-Hausdorff identity involves only nested commutators. And we see that the relation between AM and alpha and beta L just depend on the structure constants of the algebra. So let's go back. So here there is this G parameter, there is the alpha, beta, L parameter, and so on. Now, what we need, of course, is the AM as a function of all these things. Now, if you want to use the Becker-Hausdorff identity, you basically have to do commutators of these things. And that involves just the structure constants, and eventually you will get AM as a function of all these things. But to compute it, since it involves only the structure constants, you can just work out these things using a finite dimensional matrix representation of SL2R, like a 2×2 representation, and you can work it out in Mathematica if you want to. But you can use at a practical level, you can use that and work out the relation of AM to these parameters. So the next step, is to rewrite this in terms of L naught itself. So you just introduce an extra parameter, and since this is just a linear combination of the SL2R generators. Okay, so you can write this as a rotation of this L naught. Okay, so because this is like some z-axis, and you can write this as a rotation of the L naught in this particular manner. So this can always be done. Okay, so by using the adjoint action, you can always bring this AM-LM to this L naught fashion. So it can always be done, and all we have to ensure when you do this is that we have to preserve the norm, okay? And the norm in this particular case is the Cartan-Killing norm of this particular, I will introduce it again, I will define it very carefully, of this particular vector. So therefore the partition function is then, this comes out, actually this was the normal ordering constants which come out, and is basically a new temperature, just like the fact that we had the stress tensor deformation in the original case when mu was homogeneous. So it's just like a new temperature and L naught plus L naught. And this new effective temperature is the norm basically the norm of these vector, the Cartan-Killing norm of this vector. Okay, and evaluating this at least to G squared order, this is what you get. You get this new effective temperature to this this particular function. Okay, to G squared order, this is a correction. Now, okay, so we manipulate it further. Let us define this this functional without this normal ordering constant as f. And so essentially the partition function is this quantity, okay, beta effective. And the beta effective has an expansion in terms of G squared, and we know the terms in the expansion in principle. And to G squared order, it is this. You can see this is the G squared order. And so we have the partition function, and the deformed partition function up to alpha. And using this, we can just, we can evaluate the Rene divergence. And here's the formula for it. And you see this term which came about, this term which I'm circling. This term was exactly the same term as you saw for the deformed harmonic oscillator. Okay, there are other features of the theory. There, you know, in the harmonic oscillator we had some omega and mass and so on, but here it's basically the undeformed partition functions derivative. But this particular, the dependence on alpha at this order is sort of the same. It's exactly the same actually. Okay, and
Yes. I have a small question.
Yeah.
So this seems to be like a mixture of the alpha parameter seems to suggest that you are taking a mixture of deformation or.
Okay. Yeah, I mean, as I said, it is an Euclidean quench. The partition function has, you know, is turned on. I mean, the deformation is turned on for alpha at beta time, and 1 minus alpha beta time, it is turned off. But you know, this result is a result of the calculation, not any assumption actually. So, but for instance, in the original case, the homogeneous deformation case, the ones which we discussed earlier, in which the deformation is commuted with the Hamiltonian, the formula was not as complicated as this. It was it was a different expression we got for the alpha dependence there.
So does this generalized expression, does it has any physical significance as far as
yeah,
the deformations?
we just used to study the generalized second laws of thermodynamics.
Okay.
But you know, yeah, in fact, since it's very universal, I mean, and this is a part of the CFT which is there present in any CFT,
Okay.
right? I mean, this L0, this part of the algebra is present at any 2D CFT, right? So this should be there. I mean, if at all we evaluate this, this will be there in any CFT actually. And in particular, that's the reason. I mean, the reason for looking for such things is that, you know, this is the like sort of the global part of it, or the stress tensor part of it, which most probably can be seen in gravity.
Okay. Sure.
I mean, that is sort of the motivation for studying it, actually.
Okay.
Yeah. The gravitational setup, I think Myers has discussed some bit of it, but we haven't gone much further in that, actually. But the motivations to study, I mean, to get these quantities are for that. You can see that, you know, right from the harmonic oscillator to this, even it's the same function.
So if one has some sort of dynamical horizon setups in gravity. And there is a dual CFT descriptions.
Yeah, I don't know how to set it up actually. Yeah, this thing, like it is an Euclidean quench, you know. The usual one is there's a shock wave and then there's some other temperature after that, and so on. That is known, but one has to think about how to set this up. Okay. I haven't thought about it very much.
Okay.
Actually.
Thank you.
Yeah. Now, as a check, actually, in fact, originally we did this by perturbation theory, and the referee is the one who pointed out we can do this abstract analysis, actually. We have actually done this in perturbation theory first, and we, of course, got the same answer. But this abstract analysis was suggested by the referee. And we can do this, we can actually repeat this also for spin 3. And in fact, when you do for spin 3 with this deformation, again, we get the same functional dependence. Actually, the scaling here is different. So we get the same functional difference. In fact, for spin S, is some, this basically these same factors come out. Okay. So it's universal for this deformations, actually. And the reason for this universality comes about when you study perturbation theory. And when you study perturbation theory, the universal reason is because of this algebra. You see, it's CFT times LK, which is L plus and L minus, gives this particular relation. Similarly for the Ws, CFT is L naught basically, and the harmonic oscillator. So because of this universal, I mean, and if you see, do the perturbation theory, you can see the structure emerging actually, that it is because of this universal algebra that the alpha dependence is universal. Now, so that sort of concludes my, part in which I discussed about, deformations of the density matrix, thermal density matrix itself, and studying Rene divergences out of that. So now I will move to the original question, actually. The question in which we have not fully finished, and we have part answers, actually. So I have 10 minutes. Is that okay? I mean, hello?
Yeah.
I can go ahead, right? I mean, a little bit extra time. I mean,
yeah, sure.
Yeah.
Continue.
So yeah. So now we will talk about entanglement entropy and relative entropy of Virasoro descendants. So this is also a similar question in which we are, we are changing things by the symmetry generators of the theory itself, and seeing how information theory, observables change. Now let's just try it out. So suppose we have a density matrix, as we saw of primary of weight. Oh, this was what was our focus initially, and we look at the descendant. We look at the descendant of this kind. So what is the entanglement entropy of the single interval for this excited state, and how does it compare with the primary? Okay, that's the simplest question we can ask. And surprisingly, it has not been addressed. After so many studies, it has not been addressed. And there is some structure, as you will see towards the end. Okay, so suppose we just try to evaluate it, right? This is just the level 1 descendant. So recall, so to evaluate the entanglement entropy, one needs to evaluate the 2 endpoint function on the uniformized plane. That was the first, how we started out with. So we will need a conformal transformation of the descendant because you remember we had mapped it to the uniformized plane, and then there was this conformal transformation. Okay. So the descendant has a more complicated conformal transformation. So it is of this kind. Okay, you can evaluate it just by the definition. You can evaluate this transformation. Okay. Now, so instead of one term, which is previously we just had something, a term of this kind actually, just this slope was there, but now the second derivative of the conformal transformation comes into play. And this means now we will have to evaluate, 2 to the 2n endpoint functions on a branch planes and put them together and take the n going to 1 limit. So it's a more complicated object actually. Even this level 1 descendant. Okay. Now let us address for the simplest question again. So in that original problem, if you remember, the primary had no entanglement, extra entanglement compared to the vacuum. It was a surprising result, but it had no entanglement. But let's look at the descendant now. So here's the descendant, and then we know the original correlators. This is for the primary, and let us define these quantities. Okay. These are quantities basically. In fact, this is basically the slope of the conformal transformation, the first derivative, and this is the second derivative. One at 0, this is at 0, and this is at infinity. One at 0 and one at infinity. So these are the basic quantities which play the role in this. And the relevant correlator, all the correlators can be packaged in this particular fashion. Okay. It can be packaged in this where I have defined A, where I have defined A prime, B prime before. It's a complicated expression. You have defined this, and you have to take derivatives on this particular function, and then evaluate them after you subsequently take the derivatives, and then you evaluate them at the various nth roots of unity, which are where these things are located, these operators are located. Now, after several manipulations and using various identities, you can actually show that the result collapses into this form. Okay, it collapses surprisingly into this form. I mean, so here is basically the slopes of the of the conformal transformations, and the rest is the correlation function somehow just becomes this. Okay. And here is the norm. This is the norm of the descendant, actually, L to the 2n minus L squared, which is like minus 2h. If you know a little bit of the first descendant, this is actually the norm. L squared by 2 is the weight of that primary. And this is the norm of the descendant. And so everything collapses into this particular correlator. And if you think about it, it's actually the correlator, correlator of the primary del x, okay, like of the current correlator, actually. So this can happen only, I mean, after really evaluating it and then putting it at 0 infinity. Not just original correlator is not that, but this particular configuration, it collapses into this result. Okay, so then the entanglement, and so it's basically, the descendant functions like a primary in this case, and a primary del x. And so the entanglement entropy, excluding the ground state, so because we have forgotten, we have just normalized it all the time. So C is that correlator, and this is the norm. So we normalize it because we have always normalized the operators, normalize it. And you can write this whole thing in a neat form, actually, in terms of a determinant. Okay, you can write this in terms of the determinant, a 2n cross n, 2n determinant. The reason we could do this is basically because the primary was, this del x primary was done before. The two endpoint function of the del x primary was done before, and the analysis was done before. So once we showed that this collapses into that, we can just use those results. Okay, and so it becomes this determinant. And there is this particular, that determinant can be evaluated, and it's some particular gamma function. Okay, it was done earlier, actually, for that del x operator, just for the current it was done earlier. But here somehow the descendant functions like this current, and here is the entanglement entropy, actually. So there is a psi function involved. It's a complicated structure. For instance, for the primary there was no entanglement, but for the descendant, there is a reasonably complicated structure for the entanglement. And similarly, relative entropy can be evaluated. Here is the relative entropy of the descendant versus the vacuum with respect to vacuum. Here it is. And you can see from here, you can extract the entanglement Hamiltonian, and it actually looks like the weight has increased by 1. So that's the structure you see. The weight has increased by 1. Okay. And similarly, the relative entropy of the descendant with respect to with primary can be evaluated, and descendants do have. I mean, this is one would think that descendants is nothing much, but it does have relative entropy with respect to the primary. And here is the formula for that. Okay, for the Hamiltonian entanglement. So now, of course, you can't go on forever like this. This was a special case, and somehow, we've got this. In this particular case, we could do this calculation exactly, but in general, it's not possible. Actually, the 2n point in general, even for the primaries, it's not possible. So, what can you do with this thing? So we can do something called the short distance expansion. Okay, Now, so that's what I said, the level, the experience with the level 1 descendants of the simplest primary, the simplest CFT suggests there is a structure, but it's quite hard to, extract anything out of it. And you need some approximation to find more structures into it. So the question, we can address the question by looking at the short distance expansion. And in fact, it is in this approximation, which is easy to study holographically, because the entangling surface does not probe very much into the interior. Okay, so we will look at it now from the short distance expansion point of view. And for the time being, in fact, we have generalized it, but for the time being, we look at something called generalized free fields. And this is also what occurs in holographic setups. So the generalized free fields are basically when the 2n-point function factorizes into all distinct pairwise Wick contractions. So this is a very abstract conformal field theory in which the 2n-point functions are just Wick contractions, are resulted by Wick contractions, and these are believed to be holding true for systems which admit gravity to it. Okay, so therefore, in principle, we can evaluate these 2n-point functions using this rule. Okay. Now, the leading order contribution in the short distance. Okay, so suppose we want to evaluate the leading order contribution in the short distance expansion. If you think about it, it comes by pairwise contractions of the operators in the same wedge. So you remember there were n wedges all glued together to form the sheet, to form the plane, and there were pairs of operators on each of the wedges. Okay, so if you bring the operators together in each wedge, and just contract them first and take the nth power, that is the leading approximation in the short distance limit. And for that, we just need to calculate this, okay, and then raise to the power n. And that's a simple expression, and the entanglement entropy is given by this particular nice formula. Okay, now, similarly, we can, using that, you can evaluate the entanglement Hamiltonian. That's this particular formula, because the relative entropy actually vanishes. If you evaluate it in this approximation, it vanishes. And if you do it for the level 1 descendants, okay, so now it's easy. So now it's a tractable problem. So if you do it for the level 1 descendant, what you get is basically, it functions almost like a H primary of weight h plus 1, okay, but there is a correction. Okay, so there is a correction, but this correction all start out with n minus 1 the whole squared. It start out with n minus 1 the whole squared. So therefore, in the entanglement limit, in the n going to 1 limit, this doesn't contribute. Actually, this correction doesn't contribute, and it just functions as a primary of weight h plus 1. Now, this we have seen up to level 2, but actually we don't know how to prove it yet. This property that this correction to the descendant is like it's like a primary. These correlators are like primary, but they start out at higher order, n minus 1 squared order, so they don't contribute to entanglement. Now, and again, you can evaluate the leading contribution to the entanglement entropy. Similarly, the relative entropy and so on. The entanglement, basically it roughly behaves like a weight, primary of weight h plus 1. Okay, and we have seen this true for up to level 2. Okay, so there is not much structure other than the fact that it roughly behaves like weight, object of weight h plus 1. So what we can do is go to the next short leading corrections in the short distance approximation. And this correction arises from, from a sort of more general Wick contractions. Remember, the leading short distance approximation was pairwise Wick contractions on the same sheet. Now, here what you do is choose 4 sheets separately. I mean, 2 sheets, out, and contract all the operators, the pairwise operators in the n minus 2 sheets. So let us call that sheet, the 2 sheets which we left out, JK. Now there are two operators in the sheet. This is JJ prime, and two operators in the kth sheets, which is KK prime. Okay, and the possible contractions are this kind. So this one, when the operators contract within the sheet itself, is part of the leading approximation, which we have taken, leading term we have taken. Now here is this crosswise contractions, big contractions. So these are the first corrections which we can take to the short distance limit, and we have to sum over these corrections. So we have to sum over these JK, all pairs JK. Okay. And when we do that for the primary, here is the corrections. This is the correction, and you see that this term times this is the original term. Okay, and these are the corrections. Okay, to the short distance limit. And you can sum over these things and actually take then going to one limit. And here is the correction. Okay, the correction doesn't have much information other than the fact that again the dimension of the object. Okay, it has this dimension. So the entanglement entropy does not Hamiltonian. Okay, that doesn't get corrected, but here is the relative entropy. And from that structure, you can show that the entanglement Hamiltonian does not get corrected. But this is the structure of the corrections for primaries. Now, one can repeat it for the descendants. Okay, so here is the descendant. And I will talk about the level 2 descendants. Up to level 2 we have done. Level 2, there are two descendants, del squared O and O minus 2. Okay. And O minus 2 is defined by this OP. Actually, it's basically the fusion of T and O, which is O minus 2. It's a weight 2 object, actually. But it's not a primary, but it's a weight 2 object. Okay. And the conformal transformation of del squared can be found before just by using the original definition. And by some work, one can find the conformal transformation of the O minus 2 operators. It's of this kind. Okay. And from the definition of descendants, from the very construction of the descendant, one can evaluate all the correlators necessary. I mean, all the 2-point functions which are necessary. One needs only 2-point functions in this game, so at least in these approximations. So one can evaluate all the 2-point functions which are necessary. Okay, and so here is the correction. So the entanglement entropy for the first prime descendant is this gets shifted by h plus 1 as we have seen, but this one has a different structure. It has the same correction factor, but there's a prefactor, and the prefactor almost looks like the norm of this. Okay, now let's look at level 2. So here it is. So here also that kind of structures are there. So there is this. It's actually it is proportional to the norm. Here it's not quite actually proportional to the norm, but it is related in some way. Okay, to this particular. To this norms and something as I will mention soon. So there is a correction of this kind, but these factors remain the same. These shift according to the dimensions, but here there are these corrections. Now one can evaluate the relative entropy. You can evaluate various relative entropy, but what is interesting is to evaluate the relative entropies between the level 2 descendants. Now here it is, the relative entropy between the level 2 descendants. This prefactor remains the same, but this one becomes the structure. So if you do it carefully with all the results put together, you will obtain this correction. To the relative entropy. Now if you sort of know a little bit of CFT, you can actually recognize this object. So there is something called the Katz's matrix at level 2. Okay, it's basically the the matrix out of the norms of the level 2 states. Okay, and so here is the Katz's matrix at level 2. And in fact, if you carefully look at this, this correction of the relative entropy, this is the determinant of the Katz's matrix at level 2. So we have actually cross-checked, because this calculation was involved, we have cross-checked using another information theoretic measure called the trace square distance, which I didn't go very much into. but we have cross-checked this actually. So, so that's interesting structure. So the fact that you know, the information theory observables contain information about the Katz matrix. Okay. Now we can actually relax the assumption of the generalized free fields. We have not completed it, but this is the result sort of. So the OPE coefficient comes in here because OPE of OO with what is exchanged comes in, and it still gets pre-modified by this Katz determinant. So the Katz determinant is a universal factor in this game, in this relative entropy at level 2 descendants. Okay. So actually we are working, we have not finished these questions. So we are generalizing this at least to at least some of the observations to descendants at arbitrary level. And for this, there is a certain paper by Matthias actually, which Matthias Gebediel, which calculated the conformal transformations to that arbitrary level. There's a recipe for doing that. So we are trying to use, at least generalize some of these observations. And we are also working at finding the information theoretic quantities of descendants of the vacuum, which is also useful. So where can these be applied to? Actually, that is a long-term goal. Actually, we have maybe next time, I mean, in the next work or so. So the leading corrections to the short distance primaries have been used to do, you know, the following checks. So it's quite a non-trivial check. The check of, there was this proposal by Faulkner, Lukowitz, and Maldacena about corrections to entanglement entropy by considering, the bulk entanglement. And these corrections, which we are finding actually, you have to evaluate these bulk entanglement to calculate these corrections by these authors. And similarly, there is this proposal that the boundary entanglement and relative entropy equals the bulk relative entanglement entropy. And these were checked actually for conformal primaries. And in fact, these descendants are basically symmetry generators. So it'll be interesting to see how geometrically they act on these correspondences, actually, these relations in the bulk. So maybe I can just conclude by just saying, by presenting the results which I presented and saying that there are reasonably interesting structures to find by studying information theoretic quantities in CFT. Yeah, so I will sort of end with that, I think, yeah. Hello?
Yeah.
Okay.
So let us thank Justin for that wonderful talk.
How do I see actually?
If anyone has any questions, you may ask.
Sir, I have a small question.
Let me see.
So,
how do I see? I just can't see anybody. Can I at least? Okay. Anyway, go ahead. Ask your question. Yeah.
Yeah. So you introduced this Rene divergence as a distance in the thermal states, right?
Yeah. Distance between thermal states. Yeah.
Yeah. So could you write a similar thing for entanglement?
Yeah, so this distance between these states are, basically this relative entropy is a measure of distance between two density matrices. Okay. So entanglement entropy is basically something evaluated out of a density matrix, right? So you can sort of use two density matrices. That's what I've been using all the time. A density matrix corresponding to reduced density matrix of one operator, reduced density matrix of another operator, and evaluating the distance between them using the relative entropy. But if you want to make them thermal and reduced density matrices, yeah, I guess you can. But all the calculations will get complicated. Maybe, I don't know. Yeah, one can try it. Yeah.
Okay. Thank you.
But you'll have to, the interesting thing is to find results which can be checked against holography, which is what is our driving, sort of goal in this thing. Yeah. I can't see anything.
Any more questions?
Hello, Justin.
Hi. Yeah.
So regarding the statement about
Loga, right?
Yeah. This is Loga here.
I can't see anything. Yeah. Okay. Yeah.
Maybe you can just click on the Zoom icon or something down.
Zoom icon. Yeah. Somehow it's
okay.
Anyway, it's okay. Go ahead. Yeah.
Yeah. So this is regarding the statement about this thing being proportional to the Karp determinant.
Yeah.
Now I had two questions regarding that. So one is there's some positivity requirement which comes from just unitarity. So does this statement directly imply?
We were hoping actually it is just proportional to Karp's determinant, not Karp's determinant squared.
Okay.
You see, it is actually Karp's determinant squared.
Oh, okay.
Right. We were really, because this is manifestly always positive, by construction. Actually, that's the reason it's coming. But initially, when we were doing the calculation, we were actually hoping that it is actually Karp's determinant itself. So then we can use the positivity. You understand? You can use positivity of saying the positivity unitarity requires that, but it is actually Karp's determinant squared.
Okay. Okay. So I had another question, which is that does this mean that, for example, if I work in minimal models, these objects are much more easier to calculate? Like what happens when you have null states and so on?
Yeah. This null states, these vanish, right? Certain null states, this will vanish. The Karp's determinant vanish.
Okay.
Vanishes, right? Yeah. That's the condition for nullness, I think. But but this is a first correction because relative entropy is a very robust quantity. It's a quantity which is positive unless the operators are identical. Unless the two objects are identical, and this is the leading correction.
But for example, have anybody computed these objects in minimal models exactly?
No. The reason is that I think 2 endpoint functions. I don't know actually 2 endpoint functions, but there is something called the trace square distance, trace determinant squared. Trace density matrix squared. Basically, rho 1 minus rho 2 mod squared and trace. So that quantity can be calculated because that relies only on a 4-point function. And for minimal models, it's known actually. That can be calculated actually for exactly. But these quantities, the 2 endpoint functions, I think only free field theories are known. Then the current, U1 currents, del phi, or fermions, these are the things which are known. 2 endpoint functions, but nothing beyond that as far as I know.
But from your analysis, you had a formula in terms of 3-point OPEs and so on.
That's because in the short distance limit. I work in the short distance limit, and this is the correction to the short distance limit.
Okay, but from this, can you conjecture something for minimal models and check it? Or?
I don't know. We can try. Yeah, I can try because one will know this. Yeah, I can. Yeah, we'll have to look at it carefully. We are in the process of doing all these things. There are more things to be done, and
okay. Yeah. And a more broader question, which is about so this defines, let's say, between two primaries, it defines some kind of a distance, right? This information theoretic things. Like, how is this related to other things like homologicometric and so on? Is there some?
Yeah, it's not clear. This is the first thing which I have, at least I can say. This relative entropy is related to norms in some way. At least the corrections, leading corrections. In this short distance limit, you get norms of the states. The leading object is just sensitive to the weight. And then you get the norms. Yeah, I guess if you go more deeper, there will be more quantities, which you are familiar with comes in, like the OPE coefficients coming in, and so the OPE coefficients. When you take this, there is this Amarchkov metric. So it might those information gets translated like this maybe to this. That's what I can say from the explicit calculations.
Okay. Just one more question, and then I'll think so. This particular form that you have, where you have a leading order form, which is just this 1 minus x cot x, and then corrections. Is it understood, for example, if we do this similar calculations in holography?
Yes. Yeah, so that's what I want to say. Actually, that's quite a very non-trivial. I mean, people have not noticed this very much. So let's look at the primary, actually. The primary. So here it is. This is this term and this correction, right? So so this is basically the entanglement leading entanglement entropy and this correction. Now this Bellin et al., Bellin and so on, 2018 paper, they actually like set up the problem in holography. They have a primary at the origin, okay, in the bulk, and that is basically a minimally coupled scalar, but you can organize the excitations of the minimally coupled scalar so that you can pick out the primary. I mean the vacuum basically, the vacuum acted by the primary. You can do that, and then they insert this in the bulk and they calculate the corrections to the Liu-Takanagi surface. Okay, and then they also have to incorporate the bulk entanglement as given by Malderson and Lokovic and so on. And only after doing that, it's quite an intensive calculation, they get this whole thing correct, actually. So they could reproduce this, but they have to use the full thing. They have to use this bulk entanglement. This is one of the really stringent tests of this Liukowitz-Malderson and Faulkner proposal, that the bulk entanglement contributes. So they have to do the one loop corrections, and then they actually, they reproduce this factor.
So is the
statement, they do it numerically, by the way, they can't get it analytically.
So is the statement that this correction is actually dual to one loop?
Yeah, not exactly. So there is many combinations. So for instance, when you insert this state in the bulk, then the Liu-Takanagi surface also gets corrected. So there's a correction from there. Then there is also the bulk. So everything combines in a very interesting way to give this this thing. Yeah, okay. It's non-trivial. It's like, it's worth a sort of general club, that paper. Actually,
Okay, thank you.
Yeah.
Hi, Justin. This is Surbhi.
Yes, yeah.
So in your initial setup, you had these states at temporal infinity.
Right, yeah.
So, I mean, you might be familiar with my question that could you think of this also with states at spatial infinity and think of the...
doing this, I didn't think about it, So I guess then it will relate actually to question somebody else asked about having thermal states and entanglement for that. I think because it's a thermal state, right? It's a thermal but deformed thermal states. With these things.
But I mean, my question was that what sense do these descendants make then? And does it make sense to compute the relative entropies and all those things?
Yeah, I mean, one has, I don't know what results we will get, but one can do these these calculations. One can actually,
And then the bulk is also tractable with the...
but one has, one can do the CFT at least. The bulk, even this one, it will be very interesting to get the descendants in the bulk, because it's how symmetries act in the bulk, right? So that will be interesting to see to come out.
Okay, thanks.
Okay, more questions? Okay, if not, let us thank Justin again. We'll see you guys next time.
Yeah.
Thanks, Justin.